time I'm in this part of the presentation. Yes, a great experience. Can you hear me? Yes. So I will try to speak slowly. I'm originally Danish. I was taught in English, Danish, but I prefer it in English. So what I'm going to go is just to slowly, they gave me an hour and a half. So and so I'll try to give you some ideas of this, what this work of cloaking is. So let's first say I want to talk a little bit about the electromagnetic part of it. Is of course we're looking at solving the Maxwell's equations, and so let's just repeat it early in the morning. So the Maxwell's equation says that you have a magnetic field. You take the curl of the magnetic field. You have a permeability, the curl of, let me take them in the other order. You take the curl of the electric field, so E is the electric field. It's in a dielectric. It doesn't have to be conducting. It could be in the air, but it supports an electric field and a magnetic field. And so you have the curl of E is equal to the time derivative of the magnetic field. And this one here characterizes your medium. Your medium, this is called the permeability. It characterizes, it's different from different materials. So this is a material-dependent constant. This is the first Maxwell's equation. The other one says that the curl of H is equal to, and now you can have something that conducts currents or doesn't conduct current. Let's say you have something that conducts currents, then you have a free current. Free current means electrons move around, there are charges moving. And then you have a permittivity, which is an electric property, and it says something about the electric properties of the materials. And then you have ddt of E. So these are this is a classical vectorial way of writing the linear Maxwell's equation. And these things here are the material-dependent constants. They could depend on where in the material you are. And this is a free current, which again is related to the magnetic field, the electric field. So typically, the model for this is that the free current is equal to the conductivity times the electric field. So you have a relation between the electric field and the current, and there is something that's called the conductivity of a metal or whatever, and these are sort of the equations. Now, funnily enough, these Maxwell's equations, of course, carries Maxwell's name because he studied electromagnetic. They were actually, I think, more or less formulated this way by Heaviside, and Heaviside only got the name on Heaviside function, but he was a very interesting character. So that's actually, I'm going to look, in this talk, I'm going to look at a very special version of it. I'm going to look at what I call time harmonic. So because I don't want you to see where does this equation come from. So it's a special solution to the Maxwell's equations. I want to look at time harmonic, and that means that I want to look at solutions of the form E omega t. Omega is a frequency. E I omega t times E of x, or E minus I omega t h of x. That's going to be my E, and that's going to be my h. So I'm going to specify very special oscillatory behavior in time, and this is, of course, a frequency. So this is what you would call its signal frequency, time harmonic. So that's the time harmonic, you take it at 1. So it's if you think of the Maxwell's equations, one of the electromagnetic waves is, of course, light. What we are modeling here is monochromatic light at 1 frequency. So it could be microwaves, it could be, it could be any kinds of. So if we now introduce this here, so let's introduce E as this. So then we get the curl. So the curl of E, and now E means just this function of x. So it's just a function of x. Then, of course, I get e to the minus I omega t out here. I'm going to cancel that eventually so that I get an equation, because I'll have a factor e to the minus it on both sides. So I get this is equal to, and then when I differentiate the h with respect to, I get I omega nu, and then I get h, right? Because that's what I get when I differentiate this with respect to t. I get minus I omega, and it cancels with the plus there, and so there's an h. Then I get down here, I get curl of H is equal to, and then I can write it as sigma E, if I decide that this is a relation between the electric field and the current, the free current. And then I get here minus, when I differentiate this thing here, I get minus I omega epsilon, and then I get E, right? That's what I get. Okay, now let's reorganize that a little way. Let's divide through by mu. So I do like this. Then we have this thing here. Then let me multiply this by I omega. So then I get I omega. And then I get I omega squared. There's an omega squared, and the I squared is a minus 1, which goes with a, so I get a plus 1 omega squared, right? That's what I get out of that calculation. Now what I do is I take the curl of this equation. So if I take the curl of this equation, I get curl 1 over mu curl E. And then I have the curl of this field. These are not dependent on x, so I get this thing here, and this is equal to I omega sigma plus omega squared epsilon times E. Okay. Now the standard way, so let's take omega squared outside the frequency outside, then we get epsilon plus I sigma over omega, and then times E. Okay, so this is basically, this is a way of writing for the Maxwell's equations. If you are in the time harmonic case, this is a way of writing an equation for the electric field, just in terms of that. Now I'm going to look at a very special symmetry. So I'm going to look at a very special symmetry. I'm going to look at what's called transverse magnetic symmetry. And basically what this means is, it's the best way to remember it is you sort of think of your domain as being a cylinder. So your domain is a cylinder. And the coefficients here, the mu and the x, they are dependent on x. So they depend on x. These depend on x. Sigma depends on x. And this depends. So this depends on x. But you think of epsilon and mu and sigma are independent of x3. So this is the direction x3, and you have the directions x1, x2 here. And so everything is independent of the third variable. The fields are independent of the third variables. So whatever boundary conditions you have, whatever things you have at infinity, is independent of the third variable. And so now when you have this independent of the third variable, your solutions to these equations separate into two symmetries. You have one in which the electric field only goes in this direction. And if the electric field goes in that direction, then the magnetic field goes in the transverse direction to the cylinder. That's why it's called transverse magnetic. You have the other case where the electric field is in the transverse direction. That's called transverse electric. And then you have the magnetic field in this direction. And you can then write the solution as a sum of those two. I'm just going to assume that I have only one of them, namely the transverse magnetic. So in that case, this means that the electric field is really equal to 0, 0, and a third component that only depends on x1 and x2. And then the magnetic field will correspondingly be equal to h1 that depends on x1 and x2, h2 that depends on x1 and x2, and 0 with that symmetry. Now if you do that, then in terms of this function E3, when you write out this curl operator, the curl of 1 over mu curl of E for this particular field just becomes minus the divergence of 1 over mu, the gradient of E3 in the third component, because there's only a third component now. When you look at down here, you can see this this thing here says that this operator here is proportional to E, and E has only a component in the third direction. And so this equation is only an equation in the third direction, and in that third direction, this thing here, so I should sort of say the third component of this is really given by this. And so if you write down this equation, when everything is set, you have minus divergence 1 over mu grad E3 is equal to omega squared epsilon x plus I sigma x over omega E3. That's your equation. And that's the equation I want to look at this entire problem. That's this equation, and many times, so if you move this over here, if you were to move this over here and be equal to 0, then I would pick up a plus there, right? So I could say plus is equal to 0. That's the equation I'm going to look at. So a scalar equation, and many times when I'm not too careful, I will actually write this as divergence A grad U plus omega squared Q U is equal to 0. This is my Helmholtz equation. It has some coefficient here, and it has some coefficient there. This thing here is typically, if you could have done all of this, you could say everything that I did here was I showed you how this equation relates to Maxwell's. Of course, another way you can derive this equation is from the acoustic wave equation, just a scalar wave equation. It's a reduced wave equation. And then this thing here, the terminology for this is, for instance, typically the index of refraction. So this is your index of refraction. And it could have, as you see, it can have a complex component if your material is a metal. So this thing here is typically complex. This thing here can be complex as well. In the transverse electric case, the other transverse, this will actually be complex. So they could both be complex. This is the equation I'm going to look at. Now I have to tell you, what does cloaking mean? Well, cloaking means the following. So basically, we can observe in nature, we will observe